before we get started. Number one is we're going to do the teacher evaluation in class on Wednesday, and the science division has volunteered to be guinea pigs for using online teacher evaluations. So if you have like a computer or tablet or something, if you bring that to class so you can do it during class, you'll have like the last 10 minutes or so of class to work on it. So that's first thing. Second thing, as you saw, I finished grading exam 3 yesterday, just in time to get home and watch the Raider game, which we won again. It's not only our first winning season since I left California, but we're going to make the playoffs. I mean, we would have to lose every game and have the right teams win to not make the playoffs. So I'm pretty excited about that. Today will be the last, with the grading. My goal has been to get the exam 4 graded by Thursday, so you know before the weekend what your grade is and how much it can affect you for the final. It's going to take a miracle for me to get that done with so many tests, but I will at least give it the old college try. Final thing is, today is the last meaningful lecture because Wednesday and Friday are just going to be review. So I've got to get all of the cool music stuff in today. So with that said, let's get started. We're going to talk about sound waves. Now, sound waves are a longitudinal wave. What does it mean for it to be a longitudinal wave? Okay, perfect, Rachel. The direction that the wave is traveling is the same direction as the direction of the motion of particles. So when we had the slinky here, which I don't know where I put it afterward, but it's probably lost for good, we showed 2 different types of waves. The transverse wave, where the wave was traveling that direction, but pieces of the slinky were going perpendicular to that, or the longitudinal wave, where the wave was traveling that direction and the pieces of slinky were also moving that direction. So sound wave is the longitudinal wave. Another name for it, this is not an equivalent name, is a pressure wave. Because what's actually happening is we're having bursts of higher pressure going through air. So as I speak, I've mentioned this before, I am basically sending out pulses of air. So in slow motion, I'm blowing out little pulses. Now those pulses are coming out, somewhere about 200 per second. So you don't notice that they're coming out 200 per second, but in my throat, I basically have flaps that are going and allowing those pulses through. And so you have high pressure followed by the low pressure when it stopped the air from going through, and that's what's coming out. And so we have pressure when the sound waves are coming out, a lower pressure when they're not. So it's a pressure wave. We have 2 ways that we actually try to graph this. We graph it either with the pressure versus position or time. What in the world is that? Or we graph the displacement versus position or time. Pressure and displacement they're 2 different things. Displacement is how much the air molecules have moved from their equilibrium position. If my pin is an air molecule and the sound wave comes, when the sound wave comes, the pressure is going to initially move it out here, so it has a displacement away from its equilibrium position. And after the sound wave passes, it will come back. And actually, in the rarefaction, it'll go the other direction, and then it'll come to the center. And so the displacement is how much it's moved from its equilibrium position. As the sound waves are passing through the classroom, the air molecules, on average, they move forward, they move backward, and they come back to their position. So that's what the displacement is. And it turns out that where you have the highest pressure and the lowest pressure, you actually have the displacements are 0. It's so if you make a graph that has pressure versus, let's say, time, and then displacement versus time on the same graph, they are, and I didn't think about this, darn it, I did try to change the color. they're something like this. So they're out of phase. That is where you have maximum pressure, you have zero displacement, and vice versa. So if you look at the picture here of the speaker, we talked the last class period about sound, and you pluck a string in guitar, and then that makes sound, although we can turn it into electronic sound, and then we can make a speaker reproduce the sound. Next semester, we'll learn about how the speaker works. But out here, you have sound waves, and you have regions of high pressure and low pressure. I guess I should have put H for high there. High pressure and low pressure displayed here by colors as the sound waves travel out. So all of this to say, a sound wave is a pressure wave. It's a type of longitudinal wave, which means the motion of the particles is the same direction as the wave is traveling. In order to have sound waves, you need to have, they say three things, although I put a question mark with the listener because, well, that's a philosophical question. First of all, you have to have a sound source. You have to have something to make the bursts of pressure. And that sound source could be, something like a tree falling in the woods. The tree falls in the woods, it moves a lot of air out of the way, makes the ground move when it hits the ground, and those are what's causing the sound. The medium is what the sound travels through. A sound wave being a pressure wave, you have to have some molecules that can move for the pressure wave to go through. So that means you can't have sound in a vacuum. A vacuum is where you have no molecules. So if you watch something like, Star Wars, and they're out there and you have the TIE fighters and the X-Wings fighting each other, and you hear pew, pew, pew as they shoot their lasers, right? Well, you might hear your laser because you have air inside and it's connected to your vehicle, but unless you get hit by somebody else's, you're not going to hear that thing at all, right? Because there's no air out there for you to hear it. But Hollywood just says, well, it's a lot more fun for them to hear a battle than to just see them going like this and have no sound. And so they, either that or, what was that? Well, she said you also wouldn't see the laser. If there's no atmosphere, that's correct. We can see lasers going through atmosphere only as they scatter off of the atmosphere. So we use nice green lasers for astronomy lab because it scatters nicely off of the air. Okay, so you have to have a medium. Sound won't go through a vacuum. And then the listener, like I said, that's more of a philosophical question. For a physicist, if a tree falls in the woods and there's no one there to hear it, does it make a sound? Well, do we have a source? Yes. Was there air? Yes. We would say there was a sound, even though we weren't there to observe it. And of course, the reason we have people who ask such deep questions is that they're pondering what it means for something to exist. And to the physicist, well, it should be actually making variations in pressure, and that's what we call sound, so it should exist. Now, when we talk about sound, we talk about three things to describe it. We have the pitch, which is the frequency. So a low pitch is a low frequency, low pitch, high pitch, right? Pitch, frequency. The timbre, or the quality of the sound, is the result of the combination of pitches. So when we have the cello out here, we'll look at the combination of pitches to make the cello sound, which is going to be distinctly different from when I hum or when I whistle. So you have different timbres because you have different groups of frequencies present. And then the volume, of course, is how loud it is. And that's based on the amplitude of the sound wave. So what is the amplitude? Okay, it's the maximum displacement, how far away from the equilibrium position it goes. Okay, so let's get into these things. We describe a wave, and I have two waves described here, one Y1 and one Y2. Y is indicating the displacement or the pressure, I don't care which, because a sound wave can be described with either pressure or displacement. Y could be either one. X here is the position, and omega is the angular frequency. Now, if you look at that, what this says is my displacement depends on both the time and the position. Because when I have a traveling wave, the wave is traveling over a large range of space. It's not just a point. And as time changes at one location, I'll see, pressure go up and down, up and down. Or if I were to travel horizontally with a frozen time, I would see the pressure go up and down as I travel. So you can look at these and say, well, that seems reasonable. If I used a constant time, which in physics we call a snapshot, because if you took a picture with a camera, you'd have all at one time. Then you have, let's say time equals 0. That's constant. It's the easiest constant. And y1 is equal to a sine of kx. That's a sine wave, and it's going to repeat. Well, what is the value for the argument of sine for it to repeat? Sine of 0 is equal to sine of what other angle? Okay, I heard somebody say 360 degrees. Now, by default, when we're doing waves, we don't use degrees, we use radians. So how many radians does it take for it to repeat? 2 pi. So this is going to repeat when kx equals 2 pi. So I could make a graph. I'd have position and y, whatever it is here, and it would go like this with an amplitude of a down to minus a. And if I start here at 0, it repeats here at kx equals 2 pi. Well, if kx equals 2 pi, actually I don't need to rewrite it, I have it right there, then x must equal 2 pi over k, right? That's really advanced math right there. What do we call the distance for a wave to repeat? The wavelength. The wavelength is the distance for it to repeat. And so that means that this here must equal the wavelength for my wave. So that k, do you guys know what k is called? From like your chemistry classes, organic chemistry? Not k constant. K's are everywhere in physics. It's called the wave number. And that wave number can now be calculated as k is equal to 2 pi divided by the wavelength. So that's what the wave number is if you're like doing organic chemistry and you're doing spectroscopy and you're measuring wave numbers. That's what it is. Okay, so that was constant time. Now let's consider constant position. Which I don't know a good name for that, like snapshot. But that would be, for instance, let's say x equals 0. That's the easiest constant position to use. I could have used x equals 5. I could have used time equals 5 before, but it's easiest to use 0. y1 is equal to a sine of omega t. Well, functionally, that's exactly the same equation as I had before. I've just replaced kx with omega t. And so it turns out that I'm going to have the time for it to repeat is going to be 2 pi divided by omega. But what's the name we give to the time required for a wave to repeat? That's not the frequency, period. So that's the period, and hence we have omega is equal to 2 pi over the period, or 2 pi f, which we actually have already seen because those were definitions. One final thing on this. Let us suppose that I want to trace one part of the wave. So I have a wave, it looks sinusoidal like this, and I want to say, okay, let's take this point right here. How does that point on the wave, so the peak of the wave, how does that move with time? Well, I can determine how that moves with time because this peak here occurs when I have the argument of sine is equal to pi over 2. And so I could just say, okay, pi over 2 is equal to the argument of sine, omega t plus kx. Well, I'm going to solve this for x. X is equal to a constant. I don't care about that constant. Just going to pass by it. Minus omega over k t. If I have the equation for a moving particle, I should have position is equal to starting position, which in this case would have been pi over 2k, plus speed multiplied by time. So by matching those two, what is the speed equal to? By matching those two equations. In the purple equation, what's speed multiplied by? Time. So if I look in the top equation, what is time multiplied? It must be speed. What is time multiplied by? It's almost right. There's a minus sign there as well. So the speed is minus omega over k. Where did that minus sign come from? Because I had a positive sign here. When I set that argument equals constant and then solve for x, that's what brought in the minus sign. If I have a negative velocity by convention, that means it's going to the left. So this here, because it has the same sign for omega t as it has for kx, it's to the left. This bottom one, omega t minus kx, then when I solve for x, I'm going to have x is equal to a constant plus omega over kt. And so that one's going to have a positive speed, so it'll be going to the right. So when you have the equation for the wave, you can determine its direction by looking at the signs of the two things in parentheses. If the signs are the same, it's going to the left. If the signs are opposite, it's going to the right. And you can determine the speed by taking the coefficient of x divided by the coefficient of time. So if I gave you an equation that said y3 is equal to 2.0, let's say I'm doing displacement, so it'd be meters, times sine of 6.0x plus 2.0t, is that going to the right or to the left? To the left, because they're the same sign. And what's the speed? That's right. Now, I didn't put units in there, so we don't have the units. Obviously, in real life, you have to have units there. But that's how you'd get the speed. You can pick them off just by looking at the equation. And what's the amplitude?
Why is it 6 over 2 instead of 8%?
It's the coefficient of x,
Which is K.
which is 6 in this. Oh, wait a minute. Did I say that wrong? Ooh, I did say it wrong. I am glad to have students correct me. Omega is the coefficient of time. She is correct. It's minus 2.0 over 6.0 because I took the wrong ones. So if I wasn't sweating before, thank you. What's the amplitude from this equation? 2.0 meters because it was written out there in front. Okay, how is this going to be useful to us? If I have a left-going wave and a right-going wave that have the same frequency, same wave number, and I add them together, so here's an example of adding the y1 and the y2 that I had on the preceding page. Using the rules of adding signs, that is simplified as this equation here. So these are exactly equal to each other. But we see this has a time-dependent portion, and it has a, really change color. It has a space-dependent portion. So when we have these two waves, we can separate the time and the space parts. And so that means that I'm going to have, if you look at this picture, it's illustrating what you get for the outcome. There are going to be positions where sine of kx is equal to 0. Right? When kx is 0, when kx is pi, when kx is 2 pi. At those positions, then I'm going to have 0 for the spatial part. And so those positions where we're going to have 0 are marked here as with an N. N stands for node. So the node is where you have no displacement. It actually works out. It's a mnemonic there. Nodes are no displacement. Now, everywhere else, there will be some displacement. And at the places where kx is equal to pi over 2 or 3 pi over 2 or 5 pi over 2, or etc., then this term sign is going to be equal to plus or minus 1, and we'll have maximum displacement. And so those places are marked A, and A stands for antinode. And what the antinode means is these are locations where you have maximum displacement, where you're going to have the most motion. So if this is two waves traveling on a string, they come together and they interfere, and we're going to have maximum interference here at the antinode. So the string is going to move up and down with the biggest amplitude there, and we'll have no motion at all at the nodes. So we call this a standing wave. And these standing waves are the key to us being able to make musical instruments. We make musical instruments, and if I have something like a stringed instrument, I'm going to have Jordan in just a few minutes come up to play his cello for us. Well, he's not going to play beautiful music. He's going to, for the most part, intentionally play non-music for us. He has a string that's attached at both ends so that it can't move. If you're going to set up a standing wave on that string, a standing wave is going to be a wave where if you drive it at that right frequency, the amplitude gets bigger and bigger, resonance occurs. What do we call the positions where the string doesn't move? Nodes. So there's going to be a node at each end of the string. That has to be true because it's fixed in those positions. And that means there's only going to be certain wavelengths that will set up a standing wave on that string. Hence, there are only certain wavelengths that it can resonate at. So the longest wavelength that will resonate we'll call the fundamental. So this top one is the fundamental. And it has a node at both ends. How much of a wave fits if you go from a node to node in a standing wave? I'm actually going to go back here. If I go node to node, how much of a wave do you have there? I'll trace a wave. That's right, 1/2. So that means in the fundamental here, I have length is equal to 1/2 wavelength for the fundamental. But for the next one, to go node to node for the next shorter wavelength that will resonate, I now have a full wavelength. So for the next one, I have L is equal to, and I write this in the very provocative 2/2 form. 2/2, clearly 2/2 is 1. For the third one, what do I have? How many wavelengths do I have for the third resonant frequency? 3/2. So in general, I could say the length that resonates is equal to, N/2 lambda. But here's the thing. I put a subscript N for the length, saying if I have a certain wavelength, these are the lengths that can resonate. But if you have a musical instrument, the length isn't changing, right? What's changing? The length of the string isn't changing. What is changing for the different frequencies that will resonate? Different question. It's the wavelength that's resonating. And so I should put a subscript there on the lambda because there are different wavelengths that will resonate on one string. Well, given that I have this relationship now, this length of string will resonate at these different wavelengths, then I'll just solve that for the wavelengths that will resonate. So I just solved it for lambda, and then put it into our equation that says speed is equal to frequency times wavelength. So the speed is equal to the nth frequency that resonates multiplied by the nth wavelength that resonates. And then let's solve that very quickly for the frequencies that will resonate. So it turns out the frequencies that will resonate on this string are n times v over 2L. What is n here? I didn't define it when I first wrote it down here. What was n? N was the number of antinodes. But it was a counting number. It was 1 or 2 or 3, etc. So n was any positive integer. So that means that the frequencies that will resonate are equal to n times a fundamental frequency where the fundamental frequency is equal to v over 2L. So that's our condition for resonance on a string. Now, of course, the speed, what is the speed in this equation? It's actually not the speed of sound. It's the speed of the wave on the string. And it wasn't a sound wave on the string. So it's the speed of the wave in the string on the string. And it turns out that the speed of the wave on a string is equal to the square root of the tension divided by the force per unit length on the, or not force per unit length, the mass per unit length of the string. So if you tighten the string, what does that do to the speed? Increases it. And if you increase the speed, what is that going to do to the fundamental frequency? Increase it. What about if I use a heavier string? Because when we look at Jordan's instrument, he has some strings that are heavier than others. That is, they're thicker. So they have a higher mass per length. What's that going to do to the speed? Slow it down. And then what's it going to do to the speed? Or excuse me, we already said that. So what's that going to do to the fundamental frequency then? Lower it. So you have the different strings with different masses per length. So you can have similar tensions on the strings, but have different fundamental frequencies. And how do you tune it, Jordan? Tighten and loosen. So we'll have him do that when he brings the instrument out. Okay, our first clicker question. What is the boundary condition at the end of a guitar string? And after you finish this, Jordan, come on up. Okay, let's see how we answered. Okay, the boundary condition at the end of the string, the majority of people are correct. The majority of people said the displacement must be 0. If you look at Jordan's instrument here, his string goes from the bridge where the strings can't move to, what do you call it there?
Top of the neck.
The top of the neck. Excellent. He and I are in cahoots on lack of knowledge about the technical terms. Okay, so the two ends are fixed. So the displacement is 0, and if it's going to set up a standing wave, then it's going to be an antinode. Now what I'm going to do here is we're going to sample what the sound wave looks like when Jordan plays on the instrument. So we have two displays. The one on the left is showing frequency. The one on the right is actually showing the pressure as a function of time. So go ahead and just play a nice note. Darn it. I tried to. Come help me. Just hold this over here so I can pick up the sound pretty well, and I'll stop it. So go ahead and play something, Jordan. Okay. If you look at this wave that he made, it doesn't look overly pretty, does it? It's not a nice sinusoid. But you can see that it has some repeating things. First of all, looking at this, in what ballpark would you say the period is for this wave? So the wave, let's take this peak here right at the beginning. You see the hand? Of course, you can see the hand. Where does that reoccur? At approximately what time?
What is the scaling on the bottom one?
I'm having enough problems with my work here. The scale on the bottom is seconds.
And increments of what? Is it hard to see that?
I am doing such a bad job with this tool. I'm sad that I tried to pull it up. It's going 0.002 seconds per line. So approximately what time does this recur?
0.01.
Yeah, it's a little after 0.01 seconds. So this has a frequency, a reproduction for the entire waveform that is a little bit longer than you just take that time and flip it to get frequency. So actually a little bit shorter than 100 hertz. Now if we look down here, this is showing frequencies, and unfortunately we don't have good resolution down there at the low frequency, so we can't really pick out the fundamental frequency it's playing. So that's the fundamental frequency, but then there were other frequencies involved. So you look here and you see all of the little wiggles. That's a pretty high frequency. That's doing approximately 1, 2, 3, 4, 5, 6. I think there's 1, 7, 8, 9. That's somewhere in the ballpark of 18 cycles per cycle of the main frequency. Well, in the terms of music, we would call that the 18th harmonic. The harmonics are the integer multiples of the frequency in this case. They're the different frequencies that will play. So n equals 1 was the first harmonic, n equals 2 was the second. That's like the 18th harmonic. Can you play a higher pitch note?
Yeah.
Okay, so we're going to do this again with the higher pitch note. Okay. Now, if you look at the higher pitch note, you notice that on the right-hand display now, you can see that the time for it to repeat is a much shorter time, going from here like 0.004 seconds to a little bit past 0.008 seconds. So let's say 0.004 to roughly 0.009 seconds. And so we can determine the period is somewhere around 0.005 seconds, hence the frequency somewhere around 1 over 0.005, which is what? 2, is that 2,000? Help me out. You can't be 2,000 because if we look here, there's a lot of frequencies that are below 2,000. Yeah, so 200 sounds much better. So we can look here and you see here's the fundamental frequency. That's what we perceive as the pitch that he was playing. But we can see that there are integer multiples of that. So here's the next integer, the next integer, the next integer. And you can see the strength of each one of those multiples is varying. And the timbre, the quality of the sound, is the product of all of those different frequencies put together. So you can see here, if the fundamental is 200, we easily can see a strong harmonic at 10 times the fundamental. So he's got a lot of harmonics. That's what gives the cello its tone. Compare that to a whistle. Can you whistle? Okay, whistle into that thing. Okay, hold it farther away. Okay, now that whistle being fairly high, it looks kind of rough here. It doesn't look like a perfect sinusoid, but you can see that it doesn't have a lot of variation. Try low whistle. Okay, I need to be closer on this one. Okay, you can see it's a pretty nice reproducible waveform. When you whistle, it's pretty much a pure tone. It's a single frequency. And you will never get the sound of a whistle confused with the sound of the cello because of the difference there. So now, going back to the cello, let's look at what happens. Play relatively high note just because they show up better. And play the note and adjust the, adjust as you're playing. So you can adjust the tension as he's playing. You got to get closer to the little holes in it. No, not you, but yeah, for Alex. Yeah. Okay, so you see the frequencies were moving as he changed the tension because he's changing the pitch. And obviously you should have heard the change in pitch there going on with him changing the tension. And for the last thing we'll do with Jordan, let's listen to what sounds like when he plucks it compared to when he bows it. Stop. Okay, so there's what it looks like when he plucks it. That's a very different set of frequencies, a very different looking waveform when he plucks it. So that means it has a different tone and we can hear the difference. So when he's playing music, sometimes it will tell him to bow his notes and sometimes it will tell him to pluck it because they're looking for different sounds. Now, actually, I forgot. The last thing we wanted to look at was he has this thing that will try to get rid of his wolf notes. So let's hear the wolf notes.
If I can find it. Sometimes it's hard to find. There's a little bit.
Well. Okay, let's not worry. He did make the nasty sound before class, and I looked it up. And what's happened with those wolf notes is when you're playing a frequency that your actual instrument resonates with, because your instrument, it's not a string, but it also has certain frequencies that it will resonate with. And when you play one that your instrument itself resonates with, it gives you an additional resonance and it works against your sound. One last thing on this, you can't go down on that.
Did you want to give the harmonic on here? When I'm on the note in it.
Let's not worry about it because I'm worried about time. So you can go sit down too. Thanks. Thank you, gentlemen. So, yeah. Your first standing ovation there because you're standing. And okay, probably not your first. What was I starting to talk about? Oh, yes. The instrument, for it to play sound, how does the sound go from that instrument to us hearing him playing sound? It starts with the string vibrating, but then what's happening after that? Whoops. Well, in terms of the sound we hear, right, that's just the calculations we did. In terms of the sound we hear, and I have to go forward like 3 slides. Here we go. We have the string moving, and the string moves air. And if that's all we had, it would be really soft. When I was in college, the guy with the room next to me, we now will call him Doctor, he pretty much did nothing but sit in his room and plays electric guitar all day. But he did it with the amplifier off. So it was just really, really soft. Why is it soft? Because an electric guitar doesn't have a resonating chamber. The cello has a big airspace inside. And that airspace is in there because the string moves air, and so you get air pulses because of the string pushing air and then coming back. So it makes a compression when it moves out, a rarefaction as we call it. It's rarefied when it pulls in. So rarefactions are low pressure, compressions, high pressure. It makes then the air inside the instrument set up bouncing waves that go across the inside of the instrument. And the instrument has its crazy shape to give you lots of different lengths depending on what angle you go across. And that makes it so it will resonate at lots of different notes because it has different lengths, hence you can have different frequencies that will resonate. And so that chamber is called a resonating chamber, and that amplifies the sound, so you have the beautiful sound coming out. And actually, the wood should do some oscillation as well to give you a larger surface to project sound out. So those things are designed really complicated, really. Was it physicists who came up with these designs? No, it wasn't. It was artisans who just tried tweaking this and that, didn't initially know at all what the physics was, and still we aren't perfect on it because it's very complicated, but they just tried different things and found, wow, this really makes it sound good. And so if you get yourself a Stradivarius, or whatever you call it, Stradivarius, a violin, it's like super expensive because it's supposed to have this wonderful voice because of, well, how much he aged the wood, maybe, the types of lacquers he used. A lot of people have spent time trying to analyze the chemical composition of the lacquers, analyze the wood to try to reproduce to make something that sounds like Stradivarius. Okay, moving back. Another really fun thing, what we call beats. If I have two frequencies that are close to each other but not exactly the same, then I'm going to have the two frequencies at sometimes will essentially be in phase. In phase is what we call it when they're both at their high pressures at the same time. And sometimes they'll be out of phase when one's at its high pressure and one's at its low pressure. Well, what happens when I have two waves interfering and they're in phase, when they're both at high at the same time? They amplify. We have what we call constructive interference. What about when they are, one's at its high and one's at its low? Destructive. So here I have a demonstration for that. Monitor away. So I have two tuning forks. This one is unmodified. Well, that's better. So I'm just playing it, and you can see beautiful waveform that it made. The next one. Looks the same, right? Now we play them together. Why is it getting louder and softer? They're just very slightly different frequencies. So for sometimes they're essentially in phase and we have constructive interference. Sometimes they're essentially out of phase and we have destructive interference. So we call this beats. And with some pretty simple math, we can quickly determine that the frequency for it getting louder and softer is just the absolute value of the difference between the two. So let's say that you decide, I have taken physics now, I want to get a job as a piano tuner. Well, you have all of these piano strings that you have to tune, and one of the first things you have to know is what the frequencies are supposed to be for them. And then you have like one tuning fork. How do you tune all of these strings with one tuning fork? Well, you take that tuning fork and you bang it on your finger and you listen to it. You pluck a string and you adjust the tension on the string until you have the right string, the one that matches your tuning fork, until you have no beats. If you have no beats, either you're going to hear two separate notes or they're the same. So if you adjust the tension until there's no beats, you know they're exactly the same frequency. It's in tune. And you can tell, right, it's very easy to tell if you have a brief beat frequency of 1 per second. That's about what these are. They're about 1 hertz apart. It was very noticeable. So you can get it pretty much exact. And then you say, okay, now this one here is supposed to be 5 hertz away from that. So you pluck one string, pluck the next one, and you listen to get that 5 beats per second, and you adjust the tension to get that. And so you can accurately tune things, as long as the frequencies are close, by adjusting the tensions with comparison to your tuning fork or another string. Or let's say you're a pilot and you have a twin prop airplane. One of the things that's really bad if you're taking off with a twin prop is if one propeller is going faster than the other one. What would happen then? Yeah, you would not go straight. So with the twin prop, you don't have to sit there and look at the tachometers to see if they're going the same speed. You just throttle up one, then you throttle up the other, and you listen. And when the beat frequency disappears, then you know they're at the same frequency. You let off the brakes and you're going to go straight. So there's very simple practical applications of this. A simple question. Whoops. I apparently did not reset this. That's okay. So you can answer starting now. When I set up, I forgot to do that. Which type of wave is a sound wave? Okay, we should have about 6 more people answering. Wow. Okay. We had 32 who said longitudinal, 14 who said transverse, 1 that said latitudinal, and 0 that said the rest. Now, of these waves, there are 2 that don't exist. Which 2 don't exist? Okay, sideways and latitudinal. Those don't exist. I just made those up. Rayleigh and Love waves are different types of earthquake waves, seismic waves. They're combinations of transverse and longitudinal waves. So those are real waves. But the sound wave is a pressure wave, and a pressure wave must be a longitudinal wave. So sound is a longitudinal wave. We actually just saw beats in time. You can also have beats in position. Let's say that I had these were exactly the same frequency. As I walk around in the room, I could find places that are like a little bit farther from one than the other. And then they're not going to be in phase just because it takes longer to get there. So like when I was in graduate school, I used to love to go out to the Lower Granite Dam there near Washington State University. Go Cougs. Playing the Holiday Bowl, San Diego. And you could go in there where they have all of the hydroelectric generators. And they're all humming along at exactly the same frequency. It's really loud, but as you walk around, you find some places where it's nearly quiet because you're finding places where the waves are making destructive interference. So you can have beats in position as well as beats in time, like I demonstrated with the 2 tuning forks. Okay. One last thing before I get to intensity. Actually, frequencies, intensity, oh my goodness, 2 minutes to get through that. Well, as you get farther from a sound source, obviously it's not as loud. The intensity is the energy per unit area per time, or power per unit area. And so as I'm talking, sound is going out of my mouth and spreading out on a larger and larger spherical shell. Well, the surface area of a sphere is 4 pi radius squared. So the power that I'm emitting is being spread out over a bigger and bigger sphere, and hence the intensity is dropping proportional to the radius squared. So just as a general example, Rachel is about 2 meters away from me, and Paris is about 4 meters away from me. So with Paris being twice as far away from me, the intensity of the sound is 1/2 squared as much. 1/2 squared, clearly that's 1/4. So the intensity that Paris hears is 1/4 of the intensity that Rachel hears. Now, do you suppose it sounds 4 times louder to Rachel than it does to Paris? No. Our ears are not linear hearing devices. They're very logarithmic. In fact, it has to be about 10 times louder, that is 10 times more intense, for us to hear it as approximately twice as loud. So if I were to go from Rachel back to Caitlin, Caitlin hears it about half as loud as Rachel does. Okay, range that we hear. We hear from about 20 hertz up to 20 kilohertz, if you're young like you guys are. Older people will start to lose their hearing. Here is a graph that shows the acuity of hearing. Each line represents it sounds the same loudness. This bottom one is what we call the threshold of hearing. And of course, you see you can hear the best at about 4,000 hertz. The lowest intensity at 4,000 hertz is what you're going to hear. And You can see you don't hear nearly as well at 20 hertz as you do at 4,000 hertz. You don't hear nearly as well at 20,000 hertz as you do at 4,000 hertz.